Now that we have an idea of how these properties work, let's solve some questions on these few topics. So let's start with something easy. This question is just about converting temperature from one scale to another. So the first one is to convert 27 degrees Celsius to Kelvin. And then we also have from Kelvin to degrees Celsius. There is a certain mercury that has specific weight of 133 kilonewton per meter cube. Now, this mercury is at temperature 20 degrees Celsius. We are supposed to determine its density and specific gravity at that 20 degrees Celsius temperature. We know specific weight equals density times gravity. So by just making density the subject of this equation, we can calculate the density whilst we have the specific weight and gravity. Then the next thing will be to calculate the specific gravity. We know specific gravity equals density of the substance over density of water. But here we are looking at 20 degrees Celsius, and the density of water or the density of any substance is dependent on the temperature. As the temperature goes up, the density also changes. So at 20 degrees Celsius, the density is 998 kilograms per meter cube. Here we have the situation. There is a tank with interior volume of 1.5 meters cube. This tank contains air at an absolute pressure of 720 kilopascal. The temperature of the tank or the temperature of the air is 90 degrees Celsius. We are supposed to determine the weight of the air inside the tank. So weight, from what we know, is just the mass times the gravity. However, we don't know the mass yet, but we can say gravity is 9.81. So we need to determine the mass by using the ideal gas equation, because this is air. Let's solve the question in steps. So step 1, let's determine the mass of air from the ideal gas equation, where PV equals mRT. Always remember to convert your temperature to Kelvin when using the ideal gas equation. So we can get the gas constant of air from property tables, and these tables are usually found at the back of most textbooks. Also, we change the pressure from kilopascal to pascal because the gas constant that we used was given in joule per kilogram per Kelvin, not in kilojoule per kilogram per Kelvin. So we need to change the kilo of the pressure to normal pascal. So once we have the mass of the gas, then we can determine its weight. There is some carbon dioxide in a cylinder. It has a volume of 1.5 meters cubed. At an absolute pressure of 15 megapascal and temperature of 27 degrees Celsius, we are supposed to determine the mass of the carbon dioxide in the tank. So we can just use the ideal gas equation and then make the mass the subject of that equation. We can just determine the mass of the carbon dioxide in the cylinder. In this example, just like the previous one, we are supposed to determine some values of carbon dioxide in a cylinder. However, after getting these values, we are supposed to tabulate them and plot a graph using these values. So first, I think we should draw a table for the values of pressure and temperature. Then let's determine the mass of carbon dioxide in the tank. Then we can use that to determine the density of the carbon dioxide in the tank. Once we've been able to do that, we are going to use the ideal gas equation to determine the other pressures at different temperature values. So at 305.15 Kelvin, at 310.15 Kelvin, and the rest of the temperature values, we just put them in the equation and then determine the pressures at those temperatures. Then let's plot this graph using the pressure on the vertical axis and the temperature on the horizontal axis. So here again, we are supposed to determine the specific weight of carbon dioxide at 120 degrees Celsius temperature and at a pressure of 450 kilopascal. So we first determine the density of carbon dioxide by using the ideal gas equation. Then once we have the density, we can determine the specific weight of the carbon dioxide, which is thus the density times gravity. We have dry air at 25 degrees Celsius, which has a density of 1.23 kilogram per meter cube. Now, if this dry air becomes wet, then at that same pressure, the density becomes 0.65% less, which means that the density reduces by 0.65% of the original density. So at what temperature would dry air produce the same smaller density of the wet air? So let's first use the 0.65% to determine the density of wet air. Then the next step is to determine the pressure of dry air. Now, once we know this pressure, we can now determine the temperature of air that will produce that same pressure at the density, which is 1.222 kilogram per meter cube.